Hello, Calculus. It's the 22nd, so that must be Wednesday, after Wednesday's class. And I have a really big show for you today. So this revelation is nothing short of astounding. So hang on to your socks and write down this statement. If f is continuous and non-negative on an interval, closed interval a to b, then the area bounded by the graph of the function f, the x-axis, and the vertical lines x equals a and x equals b is. So go ahead and pause and get that all down, and then hang on to your socks. This is what that equals. Well, first of all, what are we talking about? Let me draw what we're talking about. So we're looking for a graph like f. Here's a function. And we'll say this is a and this is b. And it says we have a continuous non-negative function on AB. Then the area bounded by the graph, the x-axis, and y equals a and y equals b. So we're looking at this area right here. The very same sort of thing we've been looking at with all of our left boxes and right boxes and upper boxes and lower boxes and circumscribed boxes and inscribed boxes and trapezoidal boxes and midpoint boxes. All of that can be written like this. That area is the integral, we say, from a to b of the function f of x, where the variable is dx. So, if you recall, I taught you how to take some basic integrals, and then we kind of put it away, and we drew out all these boxes to find approximates, and we even got exact when we took the limit. Well, that limit, as n goes to infinity can be written as an integral. And the only thing that you haven't seen as far as integrals is this little number here and this little number here. So write that down and we'll learn more about it. This is called a definite integral. The integrals we were taking earlier were called indefinite integrals. And their answers to those were expressions. So for example, if I had the integral of x squared, previously we used our rule x to the n plus 1 divided by n plus 1 plus c. So we had a whole family of answers, because this could be x cubed over 3 plus 1 plus 2 plus 2.5 plus 1,000,000.5. So it was a whole family of answers, and it was the answer was an algebraic expression. When I put in a and b, it's called, this was an indefinite integral, because there was a whole family of answers. But when we take a definite integral, we will get one answer. Alright, we're going to build up to that, but I need to find some areas that I can do with just geometry, or pretty much geometry. So let's say I'm looking at this integral from 1 to 3 of 4 dx. Alright, so I can find that integral by looking at it geometrically. So the integral, this stands for y equals 4. The function is 4. So I'm going to sketch it, y equals 4. Right there, and I'm interested between 1 and 3. So the area goes from 1 to 3. So this area I can calculate, because it's just a rectangle, base of 2, height of 4. 2 times 4 is 8. So this answer must be 8, because I can look at it with geometry and tell. Alright. So I'll keep that one on the board, and we'll do another one that we could do. So let's do the integral from 0 to 3 of x plus 2 dx. So this time we're looking at the area under this line, x plus 2, between 0 and 3. So x plus 2 crosses here and has a slope of 2 up 2 over 1. So we have a line like that. And we're really interested in the area between 0 and 3. So we have this kind of a shape. So that kind of a shape is actually a new friend of ours. Do you see what it is? This is supposed to be a straight line. Alright, what shape is that? It is a new one. It's the trapezoid. So we know that the area of a trapezoid is 1/2 base 1 plus base 2 times the height. So let's do that in terms of this trapezoid. So we're going to get A equals, I'm not sure that's showing up, but you can hear me, 1/2. Base 1 is this value, the height of that, so it's at 0. So I put 0 in that function. I see the height right here is 2. Base 2, I put 1, 2, 3 in the function to get that value, and it's 5. And the height is really this distance, which is a 3. So what do I get? 7 times 3 is 21 halves. 21 halves is, what, 10 and a half units. So now, from using other methods, geometry, which we can't use for anything that's quadratic, because we'll have curves then, for the most part. So we used geometry to get the answer to this integral, 10 and a half. Alright, so you have that in your comp book. I need this room again, so while I erase, I am going to write out now the shocking part of our day. This is pretty shocking that all these areas that we have been doing, we could have used integrals, but we still haven't been told how to apply that A and B to actually solve the integral and come up with these numbers using calculus rather than geometry. So that is about to be revealed. I'll try to keep these integrals here. If I need the space, you have them in front of you. Alright. This is the fundamental theorem of calculus. This very day, the fundamental theorem of calculus. Alright. If a function is continuous on AB, and capital F is an antiderivative of F on AB, then, and here it is, your calculus life will never be the same. The integral, which we call the definite integral of a to b of f of x dx, equals f, that's the integral of this, evaluated at b, minus the integral evaluated at a. Alright, we're going to put that into practice to do this integral this way. So So what that is telling us to do, so if I'm going to do the integral from 1 to 3 of 4 dx, we learned earlier that the integral of a constant is 4x, and we are going to evaluate that first at b, which is the 3, and then we're going to subtract it by evaluating that at 1. And I indicate that with a line, and that tells me that I'm going to put the 3 in and then subtract and put the 1 in. So I'm going to put 4 times 3 minus 4 times 1. So I get 12 minus 4, which is 8. Notice we were expecting that all along. So the 8 right there. Alright, so now we'll try this one. I'll need that space. So this is how we find the definite integral. Fundamental to the rest of your calculus life. Very pivotal. Alright, so now let's try the second one. 0 to 3 of x plus 2 dx. Alright, we learned earlier that the integral of a sum can be the sum of the integrals. So we'll split this up into two integrals. First x, and then 2. Alright, so the integral of x is, if you recall, the thing that we're using here is in our thoughts is the integral of x to the n is x to the n plus 1 over n plus 1 plus c. However, that c does not appear in the definite integrals. Alright, so now we are going to take the integral of x using that. It's going to x to the 1 becomes x to the 2 divided by 2, and that is evaluated from 3 to 0, plus 2x evaluated from 0 to 3. So when I do that, can you remember 10 and a half? I'm going to need this space. We're hoping that it gets to be 10 and a half. So I put a 3 in, I get 9 halves. And when I put a 0 in, I get 0. Plus, when I put a 3 in this integral, I get 6. And when I put a 0 in, I get 0. So I end up with 9 halves plus 6. 6 is 12 halves. 12 halves and 9 halves is 21 halves, which is 10 and a half. Alright, as we expected. Alright, we'll practice these over and over and over and over because they have to become second nature, and that won't take very long. Alright, that's it for tonight. You can dream about that, think about it, speak about it, write about it, make poems about it, write short stories and long epics about it. But have it fresh and ready for me when we work together on Thursday. So, good night.